All right, ready to go, finally. So this is our lecture 11. I'm actually very excited about this lecture. This is a lecture that we're gonna actually get some practice. With everything that we had seen in the previous lecture, we're gonna practice a lot more. So we are going to see a new model. So it's called the constant model. We're gonna talk about some more loss functions. We're gonna try keep optimizing models and then see how this calculus thing that we started using in fitting a model is going to actually be really helpful. And then we're going to also just briefly talk about transformation. You had seen transformation before in the visualization lecture, but you're going to again see it one more time, and you're going to see how it can be really helpful in linear regression. So this is where we are. So think about this lecture as a kind of a debrief lecture plus a little bit of examples that we're going to go over so that it connects us from the previous lecture to also lecture 3. There is also going to be some homework for you to do about getting prepped for homework 3 that I'm going to tell you a little bit in the middle of the lecture. So today I'm going to start by, again, going through multiple examples, and I'm going to first start off by just reviewing what we had seen before, specifically kind of reviewing what the last piece that I quickly went over in the previous lecture that was about evaluation. So let's take a look at those pieces together. So remember when I was proposing to you the framework for creating a model, I showed you different 4 examples or 4 steps that we would go through in order to do modeling. We talked about creating a model or deciding about what kind of model or what kind of framework we want to use as the first step. We also talked about the fact that we need to measure how good of a fit our model is to each individual data point as the loss function. We had seen loss L1 and L2, absolute loss, and also mean squared loss, not mean squared loss, squared loss. And then we also talked about the fact that we need to go through a process of fitting a model or actually estimating optimum set of parameters for the model, considering that we have an objective function, considering that we have a model framework. So how do we arrive at that best fit for the model? This is a process that's called estimating parameters that we're gonna keep seeing it I think 2 or 3 times today as well. And then the last piece was always that we need to make sure that we evaluate the model so that it's not that we go through a certain process, ship the model without evaluating, without knowing what it does and how it does the task that it's supposed to do. So this is kind of the summary of simple linear regression from previous lecture. Remember, we had SLR or simple linear regression. We said that in simple linear regression, kind of similar to what you had seen in data 8, there is y-intercept that in data 100, we're going to call it theta 0. And there's also the slope. And this is the coefficient that's applied to the input. And then you're adding the y-intercept or the bias term in order to get the estimation. And we're calling the prediction y hat. And we put a hat so that we can distinguish it from the actual ground truth y value that we have. We also talked about loss function, specifically what I showed you and I derived the optimum set of parameters was using the L2 loss. When I talk about L2 loss or L1 loss, that means that I'm just looking at how I can penalize the misestimations or mispredictions for one single data point. So for one single data point, L2 loss, when you're passing me the ground truth value and you're passing me also the predicted value is going to be this squared residual value. So that's why it's called a squared loss or L2 loss or second order loss that we're always going to use. What we talked about last time was that we don't care about individual single point in our data set, but we instead care about the average error that we're incurring over the entire data set. So that's why we would go ahead and plug in what you're seeing from y hat here. We're plugging in the equivalent for y hat, which is the equation that's going to give you the y hat. So theta 0 plus theta 1 times x. And then we would say that for all the ground truth values, we would go ahead and calculate the residual between the ground truth value yi and then the residual value that we have that is calculated based on xi. There should be a subscript xi here. And then we're calculating all of those residuals. We're squaring those residuals that you're seeing. There's a square here. So it squares of the errors, and then we're calculating the mean, which is calculating 1/n times the summation of all of those scores of the residuals. What we calculated last time when we wrote this function, we called this mean squared error, or MSE, which is what it is. So just spelling out that there's mean squared squaring the errors or residuals. That's exactly what we're trying to do. What we're calling this function, we call it empirical risk, we call it objective function, we call it model risk, and different things or different ways that we're referring to this function. We are showing it by R, and this R shows that this is like the error that we're, or the average error, however we're measuring that error over the entire data set. And what we talked about last time was that this function is parameterized by theta. What do I mean by parameterized by theta? I mean that the SLR function that we had at the top is just the family of functions, right? It's just a template for all of the lines that we can have, because depending on the theta 0 and theta 1 value, I can have different lines. And therefore, because this theta value can change, and because this prediction right here can change, therefore the residual can change, and therefore the value of my error or my model risk can also change. So that's why this is a function of theta. And in this case, theta is a vector that is including both theta 0 and theta 1 as well. So you will see in the next lecture, and also at the end of today's lecture, that if I keep adding features, I'll keep adding parameters to this vector. That's why everything is shown by just theta as the annotation, or the notation that we're using here, just that it includes all the parameters that the model has. In this case, in simple linear regression, it's just two. There's theta 0 and theta 1. We also talked about at the end that we need to actually go ahead and estimate the optimum set of parameters. We did the calculus. We went ahead and calculate the partial derivative of the risk with respect to theta 0 and also with respect to theta 1. Two equations, two unknowns. We solved it, and we arrived at the fact that theta 0 hat and theta 1 hat, hat on top of the parameters, means that that's the estimated parameter, meaning that that's the optimum set of parameters that we can have, is equal to exactly what you learned before in data 8, which is theta 0 hat was equal to y bar minus the slope times x bar, and also the slope itself, or theta 1 hat, is equal to correlation times the standard deviation of y over standard deviation of x. That's the summary of last time. And we also talked briefly about visualization and evaluating and root mean square error that we need to calculate. And I'm going to briefly talk about that in the next few slides. So kind of showing you what I meant by R function, or the cost function, being a parameter of theta. So what you're seeing here in two plots is that one plot is the optimum line with optimum set of parameters, theta 0 hat and theta 1 hat. And then the other one is a suboptimal example. In the suboptimal example, what you're seeing is that I have very large residuals. If you take a look at the residuals and mentally kind of draw all of those residual values, and you, in your mind, score all of those residuals so that it is going to penalize it even more, and average over all of those scores of the residuals, you can imagine that the suboptimal line is going to have a much higher risk as opposed to the optimal line that we have. And that's exactly what we're trying to do in order to find out the theta 0 and theta 1 value that is the optimum, that passes through all of the lines as perfectly as possible. And perfect means that we want to get the minimum squared error on average on all of the data points that we have. Kind of reminding you of the terminology that I've been carefully using in the past lecture and also in today's lecture. There's a notion of estimation, and there's a notion of prediction. When I talk about prediction, what do I mean by prediction? I mean that I have an input, and I just want to plug into whatever model it is, regardless of whether it's optimal or non-optimal, and I want to get prediction. The prediction can be good, the prediction can be bad. So irrespective of that, anytime that you're getting a prediction from any model, that's called a prediction task. When I go ahead and go through the process of finding the optimum set of parameters for the model using the data, so it's called using the data, calculating model parameters. This is called estimation. So for example, when I have this simple linear regression, I would say that I go through the estimation process in order to find out theta 0 hat and theta 1 hat. And I call it estimation because we are basically estimating those parameters based on the data set that we have. And we're going to talk about how reliable this estimation is depending on your data set and how you can make sure that your estimation is as accurately as possible compared to the population of target that you have in mind. When we're doing the SLR and optimizing SLR, or every time that we're trying to minimize mean squared error, we call that we're doing least squares estimation, because we're just estimating some parameters for some model using the least squares loss function. So when you say least squares, when you hear about least squares regression, that means that it's a regression line that is optimized using a least squares function or using the MSE function. So this is kind of the terminology and where they're coming from. So once I have the optimum parameters, or irrespective of whether I have optimum parameters or not, if every time that I plug in the X value and these parameters are known, I can just go ahead and get my prediction. So that's the difference between estimation and prediction. And I just want to make sure that we're all on the same page. So again, this is kind of the summary of where we are. And the last piece that I quickly went over in the previous lecture that I'm gonna go ahead and emphasize one more time was about evaluation. Why is evaluation important? It's important because we don't want to blindly go ahead and just run regression analysis on any data set that we have. First, we need to calculate some statistics. We need to make sure that we know the mean and standard deviation correlation, more importantly, to just make sure that there is linear association before doing any kind of regression analysis, right? And if the correlation was high enough, then we would go ahead and do the modeling. We talked about root mean squared error. So root mean squared error means that I'm calculating the same MSE function that I was trying to optimize. But this time I'm going to tell you the square root of this MSE function, because what I want to do is I want to make sure that I'm reporting the error in the same unit as y. So why is that the case? For example, say that I'm predicting some length value. Length is the target that I'm predicting. If I tell you the error in, for example, meter square, it's hard for you to make sense of what that meter square is and how do you compare different models, as opposed to me going back to the meter kind of unit and tell you that, okay, the error on average is 2 meters. Are you fine with it or not? And then you would decide whether the model is accurate enough or not. It's just kind of a way of comparing different models and evaluating the performance of the model once we're done with the modeling piece. And then the last piece that I again mentioned was that we always want to visualize residuals. Remember, residual was calculated using this equation that we said that it's equal to the ground truth value minus the predicted value. So there's sometimes that the residual is positive, sometimes that the residual is negative. And what we learned from data 8 is that if we plot the residual plot, we do not want to see any pattern. The reason that we don't want to see any pattern is because if you see a pattern in the residual, that means that there was some pattern in the underlying data that you didn't model. So your model was not capturing the entire trend or the entire characteristic in the data. So you have to go back, do any kind of transformation that we'll see at the end of today's lecture in order to make sure that you literally model everything that's possible in the data so that the remaining residual is basically noise in measurement, kind of. And that's why we want to make sure that the residual plot is kind of uniformly distributed across X and also across Y, and there is no kind of pattern that we can see in the output. So I'm going to start by talking about a specific data set. I'm going to show you the demo. This specific data set is called Anscombe Quartet. There is 4 data sets in this specific data set, and we're going to take a look at the characteristics of all of these 4 data sets. So with all of these 4 data sets that we have, the mean standard, the average of X, average of Y, a standard deviation for X and Y, and the correlations are exactly the same, but the data sets are different. So we're going to take a look at what the data set is exactly. And then because our standard deviation, mean, and all of those things are the same, therefore the theta 0 hat and theta 1 hat is going to be the same, meaning that same line is supposed to pass through and model all 4 of these data sets. But what we'll see is that it's not accurate, and we could have kind of identified that it's problematic if we have visualized the data ahead of time. So I'm going to go to this demo actually, and I have I'm going to restart my kernel, and I'm going to clear all the outputs, kind of running some of these. Actually, let me reload it so that my notes are actually also reset. All right, cool. So let's take a look. So some import statements. What else I have here? This is just for adjusting the font size and whatnot on the plots. And I have a bunch of different functions: calculating a standard unit, calculating correlation, calculating a slope, intercept, fitting the least squares line by calculating theta 0 and theta 1, getting the prediction, calculating mean squared error. So all the functions that you think I would need in order to create a line and evaluate a line are implemented here. The next thing, this bunch of code is actually just doing visualization, so I'm not going to go over it, but I'm going to jump into the actual data set. So see that my data set is 4 data sets in a sense. There is X that is shared between the 3 of those data sets. So there is X and Y1, and there's X and Y2, there's X and Y3, and the last data set is X4 and Y4, and this is how they're created. X and Y1, X and Y2, X and Y3. So you can think that X is the same between the first 3 data sets, just the Y is different, and then the last data set has an entirely different X and Y. And if I go ahead and calculate, run all above. If I go ahead and calculate theta 0 and theta 1 value for all of these data sets that I'm calling them 1, 2, 3, 4, you will see that the theta 0 and theta 1 are exactly the same, and this is what we verified already. If I go ahead and try to show you why they're the same, why theta 0 hat and theta 1 hat are the same, we could actually also verify that, as I told you before, that the mean and standard deviation of X and Y and also the correlations are the same. So as I will scroll down, you can just compare all of these values that for data set 1, 2, 3, and 4, the averages, the standard deviations, and correlations are exactly the same. So what I'm going to do is I'm going to actually go ahead and try to plot these data sets so you can kind of compare them. So I'm going to zoom out slightly. I can zoom out, but this is data set 1. So you can see that, okay, there was a correlation of 0.8. So it's kind of a linear positive trend between X and Y. That's fine. For this one, the correlation says that it's 0.1, but you're seeing that there is no linear trend, but it's a higher order relationship between X and Y. With this one, it's a linear trend, but there is an outlying outlier sitting right here. And with this one, it's a line, but it's just a vertical line, and there is also an outlier. That's X4 or data set 4 that we had in the data set. So if I go ahead and just plot the line that we got, which basically had the same theta 0 and theta 1 value for all of these 4 data sets, what we will get is actually all of these lines. So you see there is this line for data set 1, this line for data set 2, for data set 3, and data set 4. So this is kind of the case that I went ahead and calculated the statistics. Correlation was high enough. I went ahead and did the modeling, but I should have visualized the data set beforehand so that I could see visually that there is nonlinear trend or there is outlier that I have to remove before doing the modeling. And because I've not done that, then the residual plots are kind of looking funny. So for this case, the residual plot is fine. So this is the residual plot that we're plotting, which is equal to residual being equal to 0, which basically means that y minus y hat is equal to 0, which effectively means that y is equal to y hat. So that's the line of perfect prediction. So if the points are on that line, that's perfect prediction. If the points are above that line, that means that there was underestimation, and then overestimation is under the line. So that's kind of how you can see. Because we know from the previous lecture that with MSE, the average errors or the average residuals is equal to 0, we should have equal number of overestimations and underestimations and so on and so forth. That's why I really want to have equal distribution above the line and equal distribution below the line, and also the same distribution across the x-axis. And we're going to see an example of that a little bit later. So this is kind of a reasonably good residual plot, doesn't show any pattern. But if I go ahead and scroll down, and I showed you the residual plot for this one, this definitely shows a pattern, which basically tells me that there was some underlying pattern in the data that I haven't captured. Maybe I should go back and do more feature engineering, and we actually have a feature engineering lecture later on in Data 100, so that I captured the entire trend in the data, so that whatever is left is kind of just noise here and not a pattern, right? That's why we don't want residual plot to have any pattern. For this one, there is still this kind of line that I'm seeing as a pattern, which is not good. For this one, the same thing. The residuals are not equally distributed across the x-axis. And that's why kind of, not the x-axis, but it's basically also showing that same pattern, that there's vertical line pattern for data set 4 that we want. So that's exactly the reason that we go through all of these processes. We calculate the statistics, we visualize beforehand, we calculate root mean squared errors, and then after we're done, we will actually go ahead and take a look at the residual plots just to make sure that is there any additional pattern that you should have extracted that you did not, so that you go back to the EDA part, do more feature engineering, and then come back to the modeling phase of your data science lifecycle. So with that out of the way, I want to jump into 2 examples. So the next 2 parts, iteration 2 and iteration 3, are going to be kind of easy. They're going to be just more practice, but they're not going to be as fun because I'm going to still do all of those derivations that are going to be a little bit not so interesting. But we'll get comfortable with it, because you have to get comfortable with these things as data scientists. What we want to train at Berkeley is data scientists who actually know all the mechanics and also all the cores of all the algorithms, as opposed to just using the black boxes from all of these machine learning frameworks, right? And you're going to gain that by going through all of these math-heavy lectures, and you will appreciate it over time, because you will understand, again, all the details and core part of the ML algorithms moving forward. So I want to move on to a simpler model, believe it or not. We're going to move back. Instead of doing simple linear regression, I want to have a constant model. So that's the model that I'll choose. And then I'm going to keep everything else the same. And I'm going to go over like how I can derive what is the optimum constant model that we can have. But let me tell you what the constant model is. And I'm going to tell you with an example. Let's assume that you work at a boba shop. There is a good boba shop by Soda that I like. And you recorded the number of boba teas that you sold over the past 5 days. And I come in and I tell you that how many boba teas do you think you will sell tomorrow? So the number of boba teas that you sold before is 20, 21, 22, 29, and 33. And the options are 0, 25, 22, 100, and something else. So let's see what you think. This is the first slide up. Let's see what you're saying. It's funny how human intuition kind of aligns with math sometimes. Not that 25 necessarily is correct, but. So kind of giving away the point of the next like 40 slides or so is that it can literally be anything. Because I haven't told you what should be your objective function, and I haven't told you what day tomorrow is, right? So you're missing that input information. But let alone if you're doing the constant model, depending on how I want to penalize your estimation, your objective function is going to be different, right? And we're going to take a look at how different objective functions might lead to different outcomes or different optimum value that you can tell. So this was a constant model. When I tell you that how many boba teas you will sell tomorrow, and I come back the day after and I tell how many boba teas you will sell tomorrow and tomorrow and tomorrow, effectively you have to have a way of measuring how good your estimation should be and how to penalize your own miscalculations or mispredictions. And you will keep telling me the same value. You will not change your information or you change your model because there is no input to your data. And you only have those 5 days and you will keep giving me the same constant value. So a constant model is a model that is also called summary statistic. It makes a lot of simplifying assumption. Simplifying assumption, for example, in the boba tea example is that it assumes nothing about the day. It assumes nothing about the temperature. It assumes nothing about, for example, whether tomorrow is cal day or not. So it basically says that no information in, I'm just going to do prediction. So it makes a lot of simplifying assumptions. And because of that, every time that you get, if you want to do prediction, it's just going to give you theta zero. Theta zero is going to be the output always, and that's the constant value. That's why it's called a constant model. As you can tell, it's much simpler than simple linear regression because there's no input, there is no theta one parameter, there's only one parameter that you're going to deal with. And the reason that I picked this model is because it's going to be simpler for you to visualize and make sense of different loss functions playing with this model and then kind of seeing the impact of them side by side. So again, this constant model always gives me, think about it as a machine. It was also a machine when we were looking at simple linear regression, but this time the machine is only parameterized by theta zero. Every time that you want to get inference, it will just tell you theta zero as the prediction. And the theta zero value is just a real value number. It's not a vector. It's just a real single value number that you will get as the predicted value. So the model is fixed. It's a constant model. The loss function, I'm assuming that I'm going to stick with the same mean squared error, and then the fun part begins. I want to do the calculus and then go through and derive and find the actual theta zero hat that is optimum for the model that we had at hand. So with the example that we had in mind, or generally with any data set, I first need to go ahead and write my entire objective function. The objective function was always that if you're thinking that you're going to use a squared loss, you have to go ahead and calculate those squared loss values for all of the data points and then go ahead and calculate the average over all of them. And again, you know that I've repeated it multiple times, that is parameterized by theta. Depending on theta zero value that you pick, you'll get a different loss value. And our goal is to find out what is the optimum theta zero that gives us the minimum cost function for the cost value for this objective function. What I've done here is that I replaced yi hat with theta zero because that makes it simpler. So my function is now a very simple function that the yi's are always given from the data set, and the only other argument that I have or the parameter that I have is theta zero. And I just need to optimize this function that is parameterized by theta zero with respect to theta zero, which means that I can just use direct derivatives. So writing it again, there are different approaches that I can do it. There's one way that I can just go through calculus, just take the derivative, find the optimum point and the minimum point, and then report that minimum point as the optimum theta zero hat value. With the data set of boba tea, because it was small enough, you could just plug in the values and just find the optimum value, right? It's just the normal calculation that you would do. But usually we don't have the luxury of having this small data set, and we would usually have millions and millions of data points. So that's why calculating directly is not feasible. For this specific case, there's also an algebraic trick that I'm not going to cover because I'm not interested in those tricks, but there is few slides at the end of the lecture slides if you want to go over and then see how you could have avoided calculus. Hopefully you will not want to avoid calculus moving on, but if you want to do that, there is an algebraic trick specifically for this kind of model because it's kind of a simple model with only one variable. So let's go through the first example because I'm really interested in just doing all of these derivatives. So this is the general case. I'm not making any assumption about my data set. I'm just writing this loss function equation that I have, or this objective function. Again, repeating that the objective function is taking the average over all of these scores of the errors, right? And what I want to do is I want to take the derivative with respect to theta 0, and then I will set it equal to 0 in a step 2, and then I will solve it in order to find theta 0 hat. That's kind of the framework that we started using in the previous lecture, and that's what we'll continue doing. But this time it's going to be simpler. Notice that instead of partial derivative, I have derivative because I only have one argument or one parameter. And technically, it's a one-dimensional function that I can just directly take derivative of. So when I take the derivative with respect to theta 0, notice that there is only this single term. So we'll keep thinking about how I can take the derivative of that single term that is hidden between multiple summations, and also it is squared as well. Remember from last time that the first step always is going to be that I can turn the derivative of a summation into a sum of derivatives, right? Because you will always be doing the derivative of a summation, because always your objective function is some summation of the error over the entire data set. So that's always going to be your first step. So I'm going to do that. I'm going to say that I'm taking out the coefficient 1 over n. I'm taking out the summation from I from 1 up to n. And then I have the derivative of yi minus theta 0 squared with respect to theta 0. Okay? So I'm going to show you one thing that I also showed you last time, that if you think about yi minus theta 0 as function f, I would call it, what I'm doing here is that I want to now take the derivative of this function f to the power of 2 with respect to theta 0. And I can use the chain rule in order to take this derivative. This is equal to 2 times function f times the derivative of function f with respect to theta 0, right? And I'm just going to go ahead and write this out and apply this chain rule. So effectively, this is going to be this coefficient that I had, 1 over n times summation of I from 1 up to n of 2 times f. What was f? yi minus theta 0. And what is the derivative of f with respect to theta 0? It is -1, because the only term that I have here is theta 0, that I would take the derivative that is non-zero, and then the derivative of negative theta 0 with respect to theta 0 is just that coefficient of -1. So I can just directly put that in. And then I'll just go ahead and simplify all of these constants, -2 over n of the summation of I from 1 up to n of yi minus theta 0. Okay, so far simple. I'll keep doing it. I'll keep taking derivatives, and you'll get comfortable with it. If I can do it in front of the class, you can just do it on the homeworks, and you will actually do it on your homework 5. It's a very fun homework, and you'll get a lot of practice with it. But you'll have to start early. Setting it equal to 0. When I set it equal to 0, what happens? So I'm finding the optimum. When optimum happens when the derivative is equal to 0. Which means that instead of theta 0, now I have theta 0 hat. So I'm going to write this as -2 over n of the summation of I from 1 up to n of yi minus theta 0 hat, this time equal to 0. Okay, and now I can just go ahead and solve it for theta 0 hat, which again is going to be that -2 over n times the summation of I from 1 up to n of yi minus theta 0 hat is equal to 0. I can just multiply two sides by -n over 2 to get rid of all of those coefficients over there, which effectively means that I can cross this out. And I'll write this as summation of I from 1 up to n of yi minus theta 0 hat equal to 0. I'll separate out those two terms. I'll turn this into I from 1 up to n of yi minus the summation of I from 1 up to n of theta 0 hat equal to 0. I can take this theta 0 hat summation to the other side so that I can get rid of the negative sign, and then I will have one term related to theta 0 hat with respect to something else. That means that I have solved it. So this effectively means that I have the summation of I from 1 up to n of yi, which is equal to summation of I from 1 up to n of theta 0 hat, which the summation of I from 1 up to n of theta 0 hat, which is a constant, is going to be equal to n times theta 0 hat, right? So then everything is going to be simple. I have one side that I have theta 0 hat and a coefficient, and I have this other side that I have a summation of the things that are known to me. I have all of those inputs, and I have all of those yi values. So I can directly go ahead and say that the theta 0 hat is equal to the summation of I from 1 up to n of yi divided by n, which we know is equal to average of y or y bar. So that's why a lot of you picked 25, because that was your initial intuition that you have to take average. And if you want to give a constant prediction, it's better that that constant prediction be the average of all the values that you already know. And you're going to see another way that it can also make sense in another way and get a different value. How are we doing? Good? Sideways? Bad? No idea what's going on? Okay, it'll make sense. To tell you the truth, these 3 lectures, you have to watch them at least twice. Maybe the next lecture, you'll have to watch it 3 times. So that's kind of the trend. But once you build these foundations, you will really be proud of yourself, because you will make use of all of these calculus that you've learned. And actually, next lecture, you will actually use some linear algebra in order to build ML models, which is really interesting. Okay, moving on. So this is what we found out. And kind of summarizing everything that we had seen so far, we had seen that y bar is my optimum parameter or my theta 0 hat. If I go ahead and plug in y bar into my objective function, this is going to give me this equation, which effectively is the sample variance, or sigma to the power, a standard deviation of y to the power of 2. What this means is interesting, but it's not necessarily useful. What I want to tell you is that in machine learning, what we're really interested in is the actual y bar value. What is the theta 0 hat that gives me the optimum value? We care really less about what that actual value is. And I'm going to show you with an example. And another reason that we care about the parameter itself and not the actual value of the cost function that that parameter is giving us is that once you have the parameter, you have the model, you can draw it, you can do prediction and whatnot. You care less about what was its performance on the original training data that you had. So that's why we care less about the value of the cost, but we care about the argument that gave us the minimum value for the cost function. And that actually has a term. So we always say that what we are trying to do in order to find out the theta 0 hat is that across all of the possible theta 0 values that we had, remember I was saying that when I give you a model, I give you a family of functions. I give you all different possible values that theta 0 or theta 1 could take. So I'm saying that across all of the theta 0 values, find the argument that actually minimizes what? Minimizes the objective function. And the argument or the value that minimizes the objective function in our case is exactly y bar. And that's what we care about. You could also argue that, okay, if I want to go ahead and just get this theta 0 that you had, or this theta 0 hat that you had, and I plug it into this objective function that I had, what is the minimum value that I'll get at the end? The minimum value that you'll get at the end is probably, or you can calculate it, that is going to be sample variance. But again, we care less about the minimum value of a function, but we care more about the argmin. Every time that you heard that, or we're calculating argmin, or we're calculating the argument that minimizes this and that, you know that it is the estimation process. And that's very important. So going back to this example, again, you saw that because in our mind, we were thinking that the loss function is MSE. If you go ahead and calculate it, that value is going to be 25, and we're good to go in that case. So Now I want to go ahead and just evaluate what had happened and what is the impact of having this constant model versus a model that can be more complex, and what's the shape of this loss function overall that we're dealing with. So the example that we're going to see in the demo is an example of a data set of dugong. So what we're trying to do is just to predict the age of dugong. In one case, I have only the ages. I'm using the constant model in order to do the prediction of the age. In another example, I'm going to go ahead and use the lengths of dugongs in order to predict the age. So that's a simple linear regression that has the lengths and the age, and then we're basically using the input, which is the lengths, in order to predict the age of each one of those dugongs. So we're going to take a look at, okay, as we simplified our assumptions, and we went from simple linear regression to the constant model, did we sacrifice anything? And what's the shape of this cost function overall? So let's take a look. So here what I'm doing is that I have this data set that I'm going to load. So the data set for the constant model, data set for the linear model. The data is also posted on Data Hub, so the data is loaded. So what I'm doing next is that I'm going to plot this cost function for the case that I have a constant model on this specific data set. So what you're seeing here is that the cost function, or this objective function, is a function of theta, right? You see that theta 0 is on the x-axis. For different theta 0 values, I have different costs on the y-axis. This is a two-dimensional loss landscape. So this is the first time you're hearing that term. You will keep hearing that term on, and every time that we're trying to optimize a model. So how did I arrive at that? Basically, I said that I'm going to just enumerate overall possible values of thetas, and I'm assuming that I'm just going to only look at the range that I think that my theta 0 hat is going to be in it. So I'm going to look at the data point, the theta 0 being from -20 to 42. And I'm going to go ahead and just build this MSE, build this constant model for the with the MSE objective function for that specific theta 0. And then I will technically take a look at that loss, and everything else is just plotting that loss for different theta values. So again, you see that for different theta values, if I go ahead and set theta 0 to be equal to 0, this is the amount of loss that I'll get. What you are also seeing in this loss function is that this is a convex function, so it curves upward, meaning that if I go ahead and take the derivative and find the optimum point, when the derivative is equal to 0, that's the point that I have the minimum. That's exactly what's happening here. That's why I was always taking the derivative. So if I take the derivative and I look at the minimum point, the minimum point should be this point. And I care, again, less about what value of loss this corresponds to, but more about what is the theta 0 hat value. It looks like that it's slightly above 10. So we'll take a look at that number. So if I go ahead and now move on to this simple linear regression, we're taking a look at the lengths and use the lengths in order to predict the age, and then we're calculating the residual in the age prediction and just building the cost function like that. So now my cost function, you're seeing that it has two inputs. It has theta 0 and theta 1. In the constant model example, the inputs to the function was only 1. So effectively, when I was plotting function r, I had theta 0 on the x-axis as the input, and then I had r on the y-axis. In this case, I have theta 0 and I have theta 1, and then that's two dimensions. And then if I want to plot also the cost value, I need to go to the third dimension. So that's why the cost landscape, or the loss surface, is going to be a three-dimensional function. I'm going to do exactly the same thing. Again, picking a bunch of different values for theta 0 and a bunch of different values for theta 1, and then just building the cost surface, or building a model evaluating a cost. This is going to be the fancy loss landscape, three-dimensional space, right? It's also kind of color-coded using this cost value. You see that when there is dark blue, that's when we have a low cost, and when it's yellow, that's when we have a very large cost. So what we want to do is we want to be really down in the valley, and we want to find out what is the optimum value that gives us that minimum point. It happens that if I rotate this, you will see the shape. This is literally a 3D surface in a three-dimensional space, right? And if I take a look at where I have the optimum, you see that my optimum is actually happening in this orange piece. This orange piece is telling me that, okay, what are those attributes of the theta hat? It says that theta 0 is equal to -44, theta 1 is equal to 23, and then z is equal to 18, which means that the cost is equal to 18. But do I care about 18? Probably no. I care about theta 0 hat and theta 1 hat. It's interesting when you compare that 18 to this value right up here, which you see that the cost is equal to 12,000. So that's why we really want to make sure that the cost of the model is less and less and exactly at the optimum place that we want it to be. So once I build those models, okay, based on the theta 0 hat for the constant model and theta 0 hat in combination with theta 1 hat for the simple linear regression, I can go ahead and calculate the square root of the mean squared error, right? Mean squared error, we have it. I just take the square root of that. And you will see that the RMSE for the constant model is equal to 7.7. That's 7.7 years of miscalculation because I was calculating the age of the dugong, right? That's a pretty much large error. As opposed to when I was looking at the simple linear regression, the RMSE was slightly better. So this kind of tells you that when I'm looking at the error in the year unit is better than year square unit. So that's why we always calculate a square root of the mean squared error, which gives us the RMSE. If I go ahead and actually do some predictions and take a look at those predictions, let's see what we will get. So we had the constant model. I had all of those age values. And definitely with the constant model, I can just draw a line or just a value, a single value using a rock plot. So you would see that, okay, in this case, it is equal to the average of all of the data points that we had. For most of them, we have miscalculation, but on average, it will work out as the best, only single estimate if I'm making simplifying assumptions. If I go ahead and do exactly the same thing with theta 0 hat and theta 1 hat, and just draw a line for the simple linear regression, you can see that it's a better estimate. That's why we had a lower RMSE. Okay, so this is kind of a comparison of what happens when your model is simple, what happens when you keep complicating your model, and then what happens with the result, how to show the result that you're getting, how to plot the each one of those functions, how to plot the loss landscape, how to make sense of what's the dimensionality of your loss function. And what did I mean by saying that this loss function or this cost or objective function is actually a function of theta, because like in one domain, we're just changing different theta values. And by changing those theta values, you have a different objective value. And then you're basically trying to optimize to get to the minimum of that landscape. So fun part so far. So we're done with these demos. So you saw all of these things that we had seen. And this is another slide question, just to give you some breather before we move on to the next example. The question is, the best estimator for a constant model with MSE loss is the mean of Y values. Sounds a little bit trivial. The answer is yes. That's what we have been talking about the past 15 minutes. So when we have a constant model with MSE, the optimum point is the optimum theta 0 hat value is actually the average of Y's. So I'm going to give you 2 minutes of break. You deserve it. But this is also with the caveat that this is your takeaway for the next lecture. You're going to go ahead and watch this 3 Blue 1 Brown video to just get some refresher on linear algebra before you come to the next lecture. But let's take a 2-minute break and then we'll be back with the next example. Okay, we're going back again. 5, 4, 3, 2, and 1. Olivia is the winner of the questions of today. Olivia is asking, do we know if a function is convex or not when we're always assuming that, oh, you take the derivative, you set it equal to 0, and you always say that that's minimum. And that's a valid concern. We always need to check for the second derivative to make sure that the function is actually convex, meaning that the optimum point is always the minimum point. And I'm going to take a look at that together with you in a second in the next few slides. Okay, so the next model, it's going to be an easy model. Now that you've gone through doing constant model with MSE, doing constant model with MAE is going to be easier. What was MAE? MAE was mean absolute error. Remember that we had the loss function, L2 loss, L1 loss. This is L1 loss, but taking average over all of the data points that we have, which we call it mean absolute error. So I'm going to take a look at how I can fit a model and how that looks like, which is a little bit tricky, but I just want you to see it at least once. So this is MAE function. So we just plugged in. What did we plug in? We just have the absolute value of the residual, which is effectively my L1 loss. And what I'm doing is I'm taking average over all the L1 losses for all I values, and I from 1 up to n in the data set that has y1 up to yn, n different data points. If I'm saying that my model is a constant model, I just need to go ahead and replace yi hat with theta 0, because always it's going to be theta 0, so we might as well want to replace it there before we do any optimization. So this is the objective function. It looks a little bit scary, particularly because this function is slightly different than the function that we had seen before. So if I take a look at for example, the L1 loss for a single data point, so what we would basically take a look at is that, okay, for this specific data point, for different choices of theta 0 value, again, notice that theta 0 is on the x-axis. I have different loss values, and it depends on whether theta 0 is less than 20 or above 20, because I have that absolute value sign. So sometimes the slope is negative, sometimes the slope is positive. So that's basically the shape of this loss function for a single data point. When I want to consider all the data points that I have right here, and I take the average over all of those absolute value functions, effectively I'll get this MAE function, that the MAE function has one of those like V-shaped functions here for 20, one of those V-shaped functions for 21, for 22, 29, and 33. And then if I sum them up together and calculate the average, what I'll get is this kind of a piecewise linear function that has multiple kinks, and the location that it has kinks is at the point that we have each one of these individual data points in our data set, right? So you would see that there is one at 20, there's one at 21, there's one at 22, and then 29, and then 33 are all of those like breaking points that we have. So this is the cost function, final objective function. It's fine. It's a convex function. It looks upward. But the issue is that this function has a different minimum point. Remember that our minimum point before was 25, which was the average. In this case, my minimum point looks to be close to 22. So we need to calculate and see how this minimum point now is different and is at 22 as opposed to being at 25. There is a second issue that this function is not differentiable. So we will see how we can deal with that. Okay, so let's take a look. We know what we should do. We use our calculus. We write this function. We would say that, okay, the first step was taking the derivative of this function, which is this coefficient of 1 over n times the summation of this L1 losses. We know that the first step is that we can turn it into the summation of those derivatives. So this is summation of all of these derivatives. But now we'll figure out that if I want to take the derivative of this absolute value function, this absolute value function is not differentiable. So we have to find kind of a workaround for it. And that's the next thing that we'll do. It's going to be a little bit kind of challenging, but it's not that challenging. So we can do it. So the first thing that I'll do is I'll say that, what if I go ahead and turn this absolute function to a normal function by just conditioning over different yi values? I would say that, what if I write this as 1 over n times the summation of I from 1 up to n of the cases that yi is greater than theta 0, the case that yi is less than theta 0, and the case that yi is equal to theta 0, right? In this case, I can get rid of the absolute value function. So I would say that this is undefined. The derivative is undefined. And we're not going to consider the case that yi is exactly equal to theta 0 for the purpose of theta 100. For the other two cases, when yi is greater than theta 0, I can just directly say that, oh, okay, my function now is going to be the derivative of yi minus theta 0, right, with respect to theta 0. Exactly because yi is greater than theta 0. So whatever is inside the absolute value function is positive, so it will be just the same value. In the other case, that yi is less than theta 0, whatever is inside the absolute value function is going to be negative. So when I take the absolute value, I should multiply it with a -1. So what I'll do is I'll say that this, in this case, is equal to taking the derivative of theta 0 minus yi, right? So this way is kind of simple, it's kind of separate, and I can move forward with taking the derivatives. So if I go ahead and take the derivatives, what will I get? So I'm taking the derivatives. This is equal to 1 over n times the summation of I from 1 up to n of, okay, what is the derivative of the first case? The case is yi greater than theta 0. Second case, yi less than theta 0. And I'm going to have a divider here so that we're not confused. Okay, what is the derivative for the first case with respect to theta 0? I'll take a volunteer from here. Tell me, what is the derivative of this function right here with respect to theta 0? Anyone is following, please? I'm hearing -1, right? So -1, because I have -1 as the coefficient of theta 0, and I'm only taking derivative with respect to theta 0. So that's the only term that will show up. So here I will have -1. What is the derivative of the second term with respect to theta 0? It is equal to 1, because that's the coefficient that I had, right? So this is the theta 0 with respect to theta 0. So the coefficient is equal to 1. So this will be equal to +1, right? So this is kind of where I'm at. So I was taking the derivative. So now my derivative is now turning into summation of a bunch of plus 1 and minus 1 values, depending on their condition, right? So if I go ahead and want to write out what's happening here, effectively what's happening here is equal to me saying that it's 1 over n times the summation of all of the cases that yi is greater than theta 0, -1, plus 1 over n times the summation of all of these other cases, not the entire set of cases that we had, because my data points are going to be divided into two options. Either they're greater than theta 0 or they're less than theta 0. If they're greater than theta 0, they're going to be counted in this case. They're going to contribute -1. If they are less than theta 0, they're going to contribute +1. So that's why this is going to be +1. But for which case? For the cases that yi is less than theta 0. That's my derivative. Okay? Sounds a little bit complicated, but things are going to get better. And you might be guessing what's happening here. And I'm just using a different notation this time when I'm just doing the derivative. So this is where we're at, kind of cleaned up version. So we're saying that we're just calculating 1 over n over two summations. One for the case that theta 0 is less than yi. One case is that theta 0 is greater than yi. But what do I need to do this time? I'm done with the derivative. I calculated the derivative. What was the second step? Doing the actual estimation, setting it equal to 0. So that's what I'm going to do. So setting it equal to 0, I'm going to actually go ahead and say, I'm going to just get rid of this coefficient right here because I don't care about that. I'll set the entire thing equal to 0. When I set it equal to 0, theta 0 will become equal to theta 0 hat. So you'll see that now my summation is equal to theta 0 hat being less than yi and is contributing, that's not a nice -1. It's contributing -1. And then for the case that theta 0 hat is greater than yi is contributing +1, setting it equal to 0. Okay? So what I'm going to do is I'm going to actually move this negative term to the other side. And then I'll try to take a look at it one more time when it's out there. So summation of theta 0 hat greater than yi. This is this term that I moved. This is equal to moving this other term to the other side is going to be equal to the summation of theta 0 hat less than yi. And this is both +1, +1. What does this tell you? It tells you that I'm counting a bunch of +1s. And the number of +1s that I'm counting in one side should be equal to the number of +1s that I'm counting on the other side, right? It's as if that I'm deciding about theta 0 and placing it somewhere that is going to divide my data set into two pieces. What kind of statistical metric or value is going to divide your data set into two equal pieces? Median is going to do that. Effectively, if my theta 0 hat is equal to median, the number of data points that are less than that and the number of data points that are more than that are going to be equal, and then that's my optimum point. And we arrived at it with the non-differentiable function, but we tried to be a little bit patient with it and calculate it under different circumstances, and then we arrived at the point that theta 0 hat is equal to median. So the rest is basically kind of exactly what I described, that theta 0 hat is now going to be equal to the median value that we wanted. And if we go ahead and plot it on the boba T example, that's going to now be equal to 22. So again, this is an example that depending on your objective function and how you would want to penalize mispredictions, you can literally get at any possible value, right? And in this case, we used MAE or absolute loss or L1 loss, and then we arrived at 22. In the previous case, we had MSE, we arrived at the mean of the distribution. So kind of summary of everything that we've seen. We talked about objective function. We talked about using different loss functions, and then what's the impact of having different loss functions in order to what final value of optimum parameters we're going to arrive at. So every time we calculated the derivative or partial derivative, we set it equal to 0, we solved it, we found out those optimum parameters. One thing that I didn't tell you, and I briefly told you, is that the function needs to be convex for the first derivative to be equal to the minimum. Otherwise, if the function is concave, the optimum point is always going to be the maximum. Sometimes when you take the derivative and derivative is equal to 0, that's a saddle point. So we always need to take the second derivative. That's also what you're going to get more practice in homework 5. And just here, the assumption is that, and we're going to show you without proof, that all of these functions, objective functions that we're defining it with the assumption that these functions are convex. And we're actually defining them in a way that the function should always be convex and differentiable, so that we can actually take derivative and do the optimization and so on and so forth, and then find the optimum minimum point of those functions. So in this case, what I'm going to do is just kind of visually compare what happened with MSE, what happened with MAE. With the constant model, because we used the single model. The only thing that was different was just the loss function that we picked. Remember the loss landscape for the MSE? That was this nice curve with the optimum point being 25. And then you saw that with the MAE, we had this other function that was piecewise linear, and the optimum was at 22. So that was kind of the difference between when we were doing the MSE versus MAE, and we arrived at different theta 0 hat values. One time the theta 0 hat was mean, one time the theta 0 hat was equal to median. The other considerations was that one function was smooth, it was differentiable. This other function was not as smooth. And then it was piecewise linear. And we're going to use some of these techniques later on in order to see how we can deal with all of these piecewise linear non-differentiable functions that we're going to have in different machine learning models. One more consideration, remember that we had two data sets in Anscombe quartet data set that had outlier, and then it was just kind of messing up with the entire modeling piece. We want to take a look at the impact of having an outlier and the choice of the loss function. So for example, in this case, you're seeing that I added a very large outlier data set, 1,033, somehow you sold that many bobatees in a day. And we're going to take a look at what that means to the loss landscape. Take a look at the loss landscape for MSE versus MAE. Remember that I was telling you that MSE is a function, or the L2 loss is a function that penalizes larger miscalculations or mispredictions more. So that's what's happening in this case. It's trying to really shift the model such that it's kind of striking a balance between predicting those smaller values that are close to each other and also having a little bit of misprediction for this large value, so that it doesn't get a very huge squared loss for that outlier value. So that's why the theta 0 hat in this case is equal to 193. As opposed to with the MAE loss, it's going to be more reliable. It's going to just slightly shift it. Again, because it's just the median that's being shifted. You're expecting that the outliers are going to be on two ends. So it's just generally going to shift your optimum point slightly to the left or to the right, but not substantially to turn it into 193. So what I would say is that MSE is more sensitive to outliers, but MAE is more robust. So that's the difference. That's the choice. If you're thinking that your data set has a lot of outliers, one thing is you remove outliers. The second thing is that use a loss function that is less sensitive, so that your predictions are not going to be so off. The other thing is the uniqueness of the solution. Say if I add another sample to your data set, previously you had 5 days, now I'm going to give you the 6th day. And I'm going to tell you that, okay, go ahead and calculate your optimum theta 0 and theta 0 hat for those cases. What you're seeing here is that with the MSE, I still have the unique solution. The unique solution is just the average of whatever data points that I have. So it's still going to be the average. It's slightly going to be different depending on this new data point that I got. But with the MAE, what you're seeing is that because I have even number of data points, I have infinitely many optimum points between the two middle points. In practice, what we would say is that we're going to take a look at the middle of those points as the value that we can use. But just know that with the MAE, it's possible that you might get a non-unique solution, or you might have multiple different values that would have the same objective function value that you can use. So meaning that you'll have different lines of the same quality. So with those examples out of the way, I want to go through transformation one more time. Remember that I was telling you that, okay, when I'm plotting the residual plot, I don't want to see any pattern. And if you see a pattern, that means that you have not done enough feature engineering, or your data was not ready for a linear regression kind of modeling that you could do. That's kind of the thing that we can fix with transformation. And hopefully by now, you're a little bit more comfortable with transformation. Remember what we had in transformation, which was that I had this Tukey muscular bulge diagram, or we had a way of thinking about how to transform different axes so that the data is linearized. So the transform version of X with respect to the transform version of Y is showing a linear relationship, which means that at that point you can use a regression line or a regression modeling for your modeling purposes. So in the case of this dugong example, although I said that, okay, I'm doing a simple linear regression and I'm happy with the simple linear regression compared to the constant model, if you go ahead and take a look at the residual plot, the residual plot kind of curves upward. So although I said that this is better than the constant model, it's still not perfect. It still shows pattern. I still need to transform my data to make my data ready for the proper modeling. So how do I do that? I go back to this Tukey muscular bulge diagram, and I would say that, okay, what kind of transformation would help me linearize my data? You would see that the pattern that I have in the data or in the residual plot is actually showing that it's a match with this quarter of this bulge diagram. And then what I can do is technically I can pick any of those transformations in order to linearize my data. So what we'll do is we'll go back, linearize our data. Once the data is linearized, then we can go ahead and just do the modeling as well. And this time, hopefully the residual plot is going to be a very nice residual plot that we can use. So again, instead of modeling Y with respect to X, meaning that I do Y equal to theta 0 plus theta 1 times X, what I can do is I can say that I'm going to take the log of Y, and I'm going to call log of Y as a variable Z for ease of use. And I would say that, okay, now I'm modeling Z with respect to X, which Z is actually now going to be the log transform version of Y, which hopefully is going to linearize my data. So going back and taking a look at how it looks like, this is the original data, original line, original residual plot. If I go ahead and linearize it, you would see that now I have log of Z, log of H or log of Y, or I'm calling it as Z, which is showing a linear pattern with respect to the input. So now the line passes through the data points a little bit more accurately. And if I go ahead and take a look at the residual plot, now the residual plot doesn't show any pattern, which technically means that log of Y is a better transformation to use with respect to the input X that I had. And now linear regression model is going to be more appropriate. Otherwise, if your residual plot shows a pattern, that means that there is some pattern in the data that you haven't captured, so you have not done good enough of a job. So what does this mean? This means that, okay, that was my data set, the data set of lengths with respect to age. I was not happy with just using this because I was seeing that the data set kind of curves upward. I did the transformation. I took the log of the age. So now I have log of the age, which I'm calling it as being equal to Z. And now the data is linear. I fit a linear regression line. So I have lengths with respect to log of age that I'm predicting, which again, this is the line. And the equation for the line is going to be, for example, something as theta, I'm going to write it at the top. It's going to be equal to theta 0 plus theta 1 times X, which X in this case is going to be my length variable. So what I can do next is that in order to go back to the original kind of scale of the data that I know X with respect to Y, what I can do is I can calculate E to the power of each side. So I can say I'm calculating E to the power of Z, which is going to be E to the power of log of Y which is going to give me y, which now I'm going to have the model that is going to be equal to y equal to e to the power of what I had here, e to the power of this equation that is theta 0 plus theta 1 times x. And now you can see that my linear regression line turned into this exponential function for me. And if I go ahead and plot the residual, now the residual actually is going to make more sense for me as well. So we're close to being done, but I just want to show you, kind of give you a primer into the next lecture. So in the next lecture, what we're going to do is we're going to use the exact same notation that we had before. So the same notation, meaning that I have inputs and features that I want to use. Then I have outputs that I want to predict. So the output is a single value, but feature can be multiple different features. And I want to go ahead and find a model or a set of theta parameters that's going to give me my predictions. And I'm going to go after finding the estimated parameters that are going to be the best case scenarios with the minimum objective function or minimum loss across the entire data set that matches my predictions well to the ground truth values. So what we will do actually is move away from only living in one feature space or one-dimensional feature space or taking only one input. And we're going to move on to the case that we have multiple different inputs. So you might have lengths, you might have, for example, weight, you might have different attributes for an instance or an object in order to make a prediction. So in that case, what we would say is that our model is going to be a multiple regression line. Multiple inputs are going to be combined together. It's still a linear regression line. And then we basically calculate a weighted average of all of those inputs in order to make a prediction. So again, our machine here compared to last time, or compared to also this time, is that we have this theta vector that is parameterized by theta theta 0, parameterized by theta 1, and theta p, assuming that you have p different features plus the biased intercept that you have. And what it will do is it will calculate a weighted combination of all of them together. It basically says that you have theta 0. It is going to multiply feature 1 with the parameter that's associated with feature 1, which is theta 1. And then also the same thing with multiplying theta 2, or the weight for feature 2 is going to be theta 2 multiplied with feature 2, so on and so forth, up until the point that you get this final prediction. So the example could be that if you take a look at my cat and you want to basically take a look at different data points of my cat over multiple years, and I have multiple different features for her. I have her length and I have her weight, and I want to go ahead and predict the age of the cat. What I can do is I can basically calculate the weighted average of all of these factors together in order to do this final prediction. This is the final thing that we wanted to go over today. So we're going to go deeper into this multiple regression. We're going to try to optimize multiple parameters together. And that's why you need to refresh a little bit on the linear algebra. Thank you so much for coming. I'll see you back on Tuesday.